Welcome to our lesson on kinematics and gravitational motion. Today we'll explore how objects move under the influence of gravity and learn the key equations that describe this motion. Let's start by understanding the basic variables we'll be working with. In kinematics, we use v for velocity, for acceleration, t for time, and s or h for displacement or height. When dealing with gravity specifically, we use g for the acceleration due to gravity, which is approximately 9.8 meters per second squared downward. Now, let's look at the three key equations of motion that describe how objects move under constant acceleration. Let's explore the fundamental equations of motion in kinematics. These equations help us understand how objects move under constant acceleration. The first equation relates final velocity, initial velocity, acceleration, and time. V equals u plus at, where v is the final velocity, u is the initial velocity, is acceleration, and t is time. The second equation gives us a relationship between velocities without needing time. V squared equals u squared plus 2as. This is particularly useful when we know the displacement s but don't know the time taken. The third equation helps us find displacement. S equals ut plus 1/2 at squared. This shows us that displacement has two parts, the part due to initial velocity, ut, and the part due to acceleration, 1/2 at squared. The fourth equation uses average velocity. S equals the average of u plus v times t. This tells us that for constant acceleration, we can use the average of initial and final velocities to find displacement. And finally, the fifth equation is for constant velocity motion. When velocity doesn't change, s equals vt. This is the simplest case where acceleration is zero. Together, these equations form the foundation of kinematics, allowing us to solve any problem involving motion under constant acceleration. Remember that each equation is useful in different situations, depending on what information you have and what you're trying to find. Now, let's look at gravitational acceleration. The equation g equals gm over r squared gives us the acceleration due to gravity at any point above Earth's surface. G is the universal gravitational constant, m is Earth's mass, and r is the distance from Earth's center. When we apply these concepts to objects in free fall near Earth's surface, we can use g equals 9.8 meters per second squared. This gives us special cases of our motion equations. V equals u plus gt, and h equals ut plus 1/2 gt squared. These equations form the foundation of classical mechanics, allowing us to predict and analyze the motion of objects under constant acceleration and gravitational forces. Understanding these relationships is crucial for solving real-world physics problems. Let's see how these equations work in practice with a simple example. Imagine we drop a ball from a height of 20 meters. We want to find how long it takes to hit the ground, its velocity just before impact, and its position at any time during the fall. Let's draw this scenario. Let's solve this step by step. First, let's identify our initial conditions. Initial velocity v0 is 0, since we dropped the ball from rest. Initial height h is 20 meters, and acceleration is negative g, or negative 9.8 meters per second squared. To find the time to reach the ground, we'll use our second equation of motion. H equals v0 t plus 1/2 at squared. Since v0 is 0 and h is negative 20 meters, we get negative 20 equals negative 4.9 t squared. Solving for t equals 2.02 seconds. Now for the impact velocity, we can use the first equation. V equals v0 plus at, plugging in our values. V equals 0 plus negative 9.8 times 2.02, v equals negative 19.8 meters per second. Finally, for position at any time, we can use the second equation again. H equals 0 t plus negative 4.9 t squared. This gives us the height of the ball at any time during its fall. Let's visualize this motion. As the ball falls, its velocity increases due to gravity, while its height decreases according to our equation. Notice how the ball falls faster and faster due to the constant acceleration of gravity. Let's summarize what we've learned. The motion of objects under gravity can be precisely described using our three equations of motion. The acceleration due to gravity is constant at 9.8 meters per second squared downward, and initial conditions are crucial for solving any kinematics problem. These principles form the foundation for understanding more complex motion in physics. Let's solve this physics problem about acceleration. A car increases its speed uniformly from 5 meters per second to 45 meters per second over a time period of 10 seconds. We need to find the car's acceleration. Let's visualize this. We have a car starting at an initial velocity of 5 meters per second and reaching a final velocity of 45 meters per second after 10 seconds. Let's list out what we know. The initial velocity u is 5 meters per second. The final velocity v is 45 meters per second. And the time t is 10 seconds. To find the acceleration, we'll use the formula. Acceleration equals change in velocity divided by time. Or written mathematically, equals v minus u divided by t. Let's substitute our values into the formula, plugging in 45 minus 5 meters per second in the numerator and 10 seconds in the denominator. Now, let's simplify. In the numerator, 45 minus 5 gives us 40 meters per second. 40 meters per second divided by 10 seconds gives us 4 meters per second squared. Therefore, the acceleration of the car is 4 meters per second squared. This means that every second, the car's velocity increases by 4 meters per second.
Constant acceleration problem. A car starts from rest and accelerates at 2 meters per second squared until it reaches a speed of 20 meters per second. How long was the car accelerating?
Let's look at the problem statement. Let's visualize this problem. We have a car starting from rest, and it's accelerating at a constant rate of 2 meters per second squared. After some time, it reaches a final velocity of 20 meters per second. To solve this problem, we'll use the formula v equals u plus at, where v is the final velocity, u is the initial velocity, is acceleration, and t is time. Let's plug in what we know. The final velocity is 20 meters per second, initial velocity is 0 meters per second, and acceleration is 2 meters per second squared. We're solving for time. Now let's solve for t. First, we can simplify the right side to just 2t. Then, to get t by itself, we divide both sides by 2. Therefore, the car was accelerating for 10 seconds to reach its final velocity of 20 meters per second.